Last week we started working on Lewis structures, looking at Lewis structures for atoms and ions, talked about the octet rule. We talked about using Lewis structures to represent ionic bond formation when a metal and nonmetal react, and covalent compounds as well. And then we also got into exceptions to the octet rule. So this recitation module will review all of those. Right, so Lewis structures, all that Lewis structures are a representation of each atom where all the valence electrons are represented for that atom with one dot. So sodium, for example, there's one dot next to sodium because sodium is a group 1 metal, and so it has one valence electron represented right here. Magnesium is group 2. It has 2 valence electrons and hence 2 dots around the atom of magnesium. So 2 valence electrons. Aluminum, group 3, has 3, right? Silicon would be 4, phosphorus is 5, sulfur is 6, chlorine is 7, all the way up to argon, where argon is a noble gas, has a full octet. So Lewis structures are just basically a pictorial representation of what are the valence electrons available to that atom, so that when an atom goes and reacts, either to form an ionic bond or a covalent compound, right, how many valence electrons do we have to lose or to gain or to share to fill the octet? Because all of these atoms are striving to be like argon. They are striving to be like a noble gas with respect to their electron configuration. They want to have a full outer shell of 8 valence electrons. So for example, if I want to talk about the reaction between calcium and fluoride to form calcium fluoride, in this example of an ionic bond forming reaction, right? Calcium reacts with fluorine. Fluorine, looking at the electron configuration of fluorine, fluorine has 7 valence electrons. So here's my Lewis structure, 1, 2, 3, 4, 5, 6, and 7. Calcium, right? Calcium is right here. It's group 2, has 2 valence electrons, so 1 and 2. And here's my other fluorine with a 7 valence electrons. So we want to think of it with respect to openings, right? It has 7 valence electrons, so it has 1 vacancy. It has 1 opening where it can accept an extra electron. So both fluorines can accept 1 more electron. So calcium, being a metal, donates 1 electron to the fluorine to the left, donates 1 electron to the fluorine to the right, and we get calcium fluoride. Calcium 2+, because it lost 2 valence electrons, and the fluorines become fluoride when they gain that 1 electron. Now, if we look at the electron configuration, fluorine, by gaining an electron, right, fluorine is right over here, atomic number 9, group 7. When it gains 1 electron, it becomes isoelectronic with neon. So fluorine reacts, it becomes isoelectronic with neon. It has a noble gas configuration. It has a full outer shell. Calcium, when calcium reacts, it loses these 2 valence electrons, the 4s2 valence electrons, and now it is isoelectronic with a noble gas. It is isoelectronic with argon. Right, here's calcium. Calcium has 2 valence electrons. It loses 1, it loses 2, right? Starts with 20, loses 2, we go to 18 valence electrons. It'll be isoelectronic with argon. Both react in a way through losing or gaining electrons to become isoelectronic with a noble gas. So here's a question from you based on that. For ionic bond formation, we have the reaction between magnesium and oxygen to form magnesium oxide. What is the configuration and Lewis structure for both atoms and ions? Right, so for you, how many electrons is magnesium going to lose, and how many electrons does oxygen want to gain? Magnesium would have the Lewis dot structure like this, right? So magnesium is neon, 3s2. Oxygen is helium, 2s2, 2p4. So the Lewis structure of oxygen, and I'll just do that in different colors so we can watch the transfer of electrons. Right, so oxygen has 6 valence electrons. Magnesium has 2 valence electrons. So in this reaction between the two, right, we're going to take 2 valence electrons from magnesium to oxygen. So magnesium is going to become magnesium 2 plus, and oxygen is going to become oxide 2 minus. For the electron configuration, right, magnesium got rid of its 2 outermost electrons. It's now isoelectronic with neon, and oxygen would also be isoelectronic with neon, right, because it gained 2 electrons. Helium 2s2 2p6 is the electron configuration of oxide, right, at 2 minus, which is the same electron configuration as neon. So here's a little bit more practice. What would the Lewis structure for fluorine, for water, and for carbon dioxide look like? Right, we can use these Lewis structures in the formation of ionic compounds and understand how many electrons would be exchanged. We can also use Lewis structures for covalent compounds as well. So fluorine is helium 2s2 2p5. So fluorine has 7 valence electrons, and I've got 2 fluorines. So I'm going to have 14 electrons to assign for fluorine. So here's 1, 2 fluorines. Got 14 electrons to assign. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and 7. Right, so both fluorines have a full octet. Both have reacted by sharing 1 electron. Both end up with a full octet, 8 electrons in their outer shell. We start off with 7. Each of those fluorines has 1 vacancy, 1 opening, so they want to share 1 electron to become isoelectronic with a noble gas. For water, how many valence electrons do we have to assign in the Lewis structure for water? Got hydrogen, which is 1s1. So I've got 2 hydrogens with 1 electron each. That's 2 electrons. And then my oxygen is helium 2s2 2p4. Got 6 electrons from oxygen. I've got a total of 8 electrons I have to assign. Oxygen goes in the middle. I'm going to connect it to both of the hydrogens. So I'm going to put the hydrogen down here and the hydrogen down here. Hydrogen has 1 electron, so here's the 1 electron from each of the hydrogens, and now I want to fill the octet for oxygen. So oxygen right now has 4 electrons, 5, 6, 7, 8. So now I've assigned 8 electrons to that central oxygen. Oxygen has a full octet. I've assigned all 8 electrons that I have to work with, and hydrogen is an exception to the octet rule. Hydrogen will never have more than 2 electrons assigned to it, so this is considered a full octet for hydrogen, having those 2 electrons in the outer shell. Right, that's isoelectronic with helium, so that's as close as, right, that is a noble gas, and that's as close as hydrogen will ever get to having 8 electrons in its outer shell. How many valence electrons do we have to assign for carbon dioxide? All right, well, carbon is helium 2s2 2p2 for 4 electrons. I've got 2 oxygens at helium 2s2 2p4, so 6 electrons for each oxygen, 2 oxygens total, so 2 times 6, I've got 12 electrons there. I've got 16 total electrons I have to assign. So again, carbon goes in the middle, and I'm going to put oxygen on both sides of carbon. And I'm going to start assigning electrons I have to work with, right? So oxygen, oxygen. So I've got 16 electrons. I just assigned 8 electrons to both of the oxygens. Both the oxygens have a full octet. And if I take a look at the central carbon, carbon also has a full octet, has 8 electrons assigned to it. What this structure would look like with respect to bonds, right? I've represented double bonds between the carbons and oxygens. There's no other way we could assign these valence electrons without making a carbon-oxygen double bond, without making 2 carbon-oxygen double bonds. So I've got 8 electrons in each of the octets, and I've got all the valence electrons assigned for carbon dioxide. Electronegativity we also covered this week. Electronegativity can be thought of as a tug of war for electron density, the ability to pull electron density toward an atom. So an atom's ability to pull electron density toward itself. And it increases from the lower left-hand corner to the upper right-hand corner in the periodic table, right? It increases from lower left to upper right-hand corner of the periodic table. So the larger the difference in electronegativity, right, the more likely that bond will be polar, because you're not going to have an equal distribution of electron density between those two atoms. So when you have a bond and the two atoms that are connected in that covalent bond have drastically different electronegativities, we'd expect that bond to be a polar bond. So of those 3 molecules that we previously drew, which one of those previously drawn molecules, right, we had fluorine, we had water, and we had carbon dioxide. Which one of those 3 is polar? And to determine that, we take a look at oxygen. Oxygen is more electronegative than hydrogen. So as a result, we're going to have a slight imbalance of electron density. Oxygen, right, being more electronegative is going to pull that electron density toward itself away from the hydrogen. And as a result of the 2 electrons that are in this covalent bond, of the 2 electrons in that covalent bond, they're going to be a little bit closer to the oxygen, a little bit farther away from the hydrogen. That puts a partial positive charge on the hydrogen and a partial negative charge on the oxygen. That imbalance of electron density, the partial positive and partial negative charges, are what make water polar. And we can see that in this electron density map here. The electron density map, I've got a greater density of electrons around the oxygen, and that creates this partial positive on the hydrogens in this ball and stick structure of water. Because oxygen is more electronegative, right? Oxygen is here with respect to its electronegativity, 3.5. Hydrogen is 2.1. That's a large difference in electronegativity, and as a result, we're going to have an imbalance of electron density. A question that came up quite often this week in lecture and in emails was, how do I know when I have the best Lewis structure? How do I know when I have the correct Lewis structure? And for that, we need to assign formal charge, right? So when we have multiple Lewis structures possible, formal charge will help us determine, do I have the correct Lewis structure? Because we want to minimize the charge. We want to minimize the charge on a molecule. We want to minimize the number of atoms carrying a charge in that Lewis structure. So here's an example of cyanide, the cyanide anion. Assign formal charges to all atoms of cyanide, right? Well, to determine formal charge, we subtract the assigned electrons from the group number. And to determine assigned electrons, we count 1 electron for each covalent bond, and we count 2 all electrons that are lone pair electrons. So if I take a look at cyanide and I want to assign the formal charges to cyanide, right, let's start with carbon. So carbon has 1, 2 electrons here, 2 lone pairs, so I count both of those. And then carbon is in 3 bonds, right? It might be easier to see over here in the triple bond, but carbon's in 3 bonds. So of that, I'm going to count 1 electron for each of these 3 bonds. So 1, 2, 3, 4, and 5. So carbon is group 4. On the periodic table, it has 5 electrons assigned to it, right? Got a charge of -1 assigned to this carbon. Nitrogen, and I dropped the lone pair here. Nitrogen is group 5. And I'm going to count the electrons assigned to nitrogen, right? 1, 2, 3, 4, 5. So 5 minus 5. Nitrogen is neutral. So here's some practice for you. Draw 2 different Lewis structures for CH2O, formaldehyde, and determine the charge on each atom in each Lewis structure. And then based on that, determine the best Lewis structure of those 2. So where do we start? We start with carbon, hydrogen, and oxygen. Carbon, right, is helium, 2s2, 2p2. Hydrogen is 1s1, and oxygen is helium, 2s2, 2p4. So I have 4 electrons from carbon. I'm going to have 2 electrons from hydrogen because I have 2 hydrogens, and I have 6 electrons from oxygen. I have 12 electrons I have to assign. So let's draw 2 different Lewis structures for formaldehyde. Right, central carbon, and I just assigned 6 electrons. So I've got 6 electrons remaining. I'm going to place my elements: oxygen, hydrogen, hydrogen, oxygen, hydrogen, and hydrogen. And now I need to assign 6 more electrons. So 6 more electrons. Well, hydrogen's all set, so I'm going to fill the octet on oxygen. Well, I also need to fill the octet on carbon, right? So next valence electron, the next Lewis structure, I'm going to draw a double bond there. That's 2 electrons, 3, 4, 5, 6. Now I've assigned 6 electrons in both of these Lewis structures. Which structure is the correct Lewis structure, A or B? And to determine that, now we need to assign formal charges, right? So formal charge, let's take a look. Carbon is group 4, and on this central carbon, I have 1, 2, 3 electrons assigned. So carbon is group 4, 3 electrons assigned. I'd have a charge of +1 on this carbon. Hydrogen is group 1, and I've got 1 electron assigned. So 1 minus 1, that's 0. 1 minus 1, that's 0. The same for these hydrogens over here. Let's take a look at oxygen. Oxygen is group 6, and this oxygen has 6 lone pair electrons, 1, 2, 3, 4, 5, 6, and then 1 electron in this single bond, so it has 7 electrons assigned. So 6 minus 7, a -1 charge on oxygen. If I take a look at the oxygen over here, I've got 1, 2, 3, 4 lone pairs, and then 1 electron in each of these bonds, so I've got 4 electrons as non-bonding, 5, 6 electrons total. So for this oxygen, 6 minus 6, that's 0. And I guess I didn't assign the charge to the central carbon, but I can do that now, right? Carbon is 4, so I've got 1 electron, 2 electrons, 3 electrons, 4 electrons assigned to it, right? 1 electron for each of those covalent bonds. So now we can see that structure B is the better structure because we've minimized charge. I've got fewer number of atoms carrying charge in this structure, and I also violated the octet rule in this structure here, right? Now I've filled the octet for the central carbon. So Lewis structure B is the best structure. Formal charge is always a challenging problem for many students, and so Here's a little bit more practice with that. So draw the 3 different Lewis structures for nitrous oxide, also known as laughing gas, and determine the charge on each atom in each Lewis structure. So I'm going to give you all 3 Lewis structures, and then I'm going to ask you to determine the charge on each of those, and each atom in each Lewis structure. So first things first, like any of these problems we're doing, right, we need to learn how many valence electrons that we have. So fortunately, we're only dealing with oxygen and nitrogen. That makes it pretty easy. So oxygen is helium, 2s2, 2p4. Nitrogen is helium, 2s2, 2p3. So oxygen, right, has 6 valence electrons. I've got 2 nitrogens, 5 valence electrons each, total of 10 electrons, 16 electrons total that I have to assign. The general structure is NNO for all 3 of these Lewis structures. All right, so I've got 16 electrons to assign. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So I've assigned 8 electrons in all of these. And now all I'm going to do is I'm going to fill the octet for the surrounding atoms. So I've assigned 8 electrons. I've got 8 electrons left. So 1, 2, 3, 4, 5, 6, 7, 8. So that one checks out. All right, I've got 6 electrons here, so 7, 8. And I've got 2 electrons on this oxygen, so 6 more. And there's my 8 electrons that I had left. And now I've just switched where that triple bond was, and so I've got 2 electrons assigned to that nitrogen. I want to fill the octet of nitrogen, so there are 6 more electrons there. And the oxygen already has 6, it only needs 2 more electrons. So those are my 3 Lewis structures for nitrous oxide. Now let's determine the charge on each of those atoms in each Lewis structure. So we've got nitrogen, nitrogen, and oxygen. Right, and I'll call this nitrogen 1 and this nitrogen 2 just to help us differentiate what we're working with. So NNO, NNO. So what would I have for charges on the first Lewis structure? What would be the correct charges there? So if we take a look, the first Lewis structure, nitrogen is group 5, and I have 1, 2, 3, 4, 5, 6 electrons assigned. So 5 minus 6 be a -1 charge. Nitrogen is still group 5 in the middle, and now I have 1, 2, 3, 4 electrons assigned. 5 minus 4 is a +1. Oxygen is group 6, and it has 6 electrons assigned. 1, 2, 3, 4, 5, and 6. So 6 minus 6, oxygen is 0. What do we have for charges assigned in the second Lewis structure? Nitrogen is still group 5. I've got 1, 2, 3, 4, 5 assigned, so this nitrogen is neutral. This center nitrogen is still group 5. 1, 2, 3, 4 electrons assigned, so 5 minus 4 be a +1. And then for the oxygen, oxygen is group 6, and this oxygen has 1, 2, 3, 4, 5, 6, 7 electrons assigned. 6 minus 7, I'd have a charge of -1 on that oxygen. And for the last Lewis structure, nitrogen is group 5, and I have 1, 2, 3, 4, 5, 6, and 7 electrons assigned. So 5 minus 7, -2 for the first nitrogen. For the second nitrogen, I have 4 electrons assigned, so 5 minus 4 is +1. And for the oxygen, I would have 1, 2, 3, 4, 5 electrons assigned. Oxygen is group 6. 6 minus 5 would be +1. We also talked about violations in the octet rule. So for example, we talked about things that may have less than 8 electrons in their octet, things that may have more than 8 electrons in their octet. And so one example of that is boron. We said that boron will always only have 6 electrons in its outer shell. So what is the Lewis structure of boron trichloride? And to answer that question, how many valence electrons do we have to assign? Right, so first I'm going to start with boron, and then I'll get to chlorine. So boron is helium, 2s2, 2p1, right there. Chlorine is neon, 3s2, 3p5. I've got 7 valence electrons from chlorine, and I've got 3 chlorines, a total of 21 electrons from chlorine. And I've got 3 electrons from boron for a total of 24 electrons to assign. I'm going to put my boron in the center, because it's less electronegative than chlorine, and I'm going to connect boron with the 3 surrounding chlorines. So I just have 24 electrons, and I just assigned 6 of those electrons, so I've got 18 electrons remaining. All right, I'm going to fill the octet for the surrounding atoms, so I've got 6 electrons here. I've got 6 electrons here for 12, and then 6 more here for a total of 18 electrons. So I have no remaining electrons. That being said, I have not filled the octet for boron, right? Boron has 2, 3, 4, 5, 6 electrons assigned to it, and that's fine. This is a valid Lewis structure for boron, right? Because boron will never have more than 6 electrons in its outer shell. So boron violates the octet rule on the low end of that count. We also talked about structures that violate the octet rule on the high end, so greater than 8 electrons, and we said that those atoms that can violate the octet rule on the high side need to be row 3 and beyond, so beyond phosphorus. Because in my third row, when n equals 3, I have s orbitals, I have p orbitals, and for the first time, I have d orbitals. Right, I can hold 2 electrons in my s orbital, I can hold 6 electrons in my p orbital. There's 8 electrons, so if I have to hold more than 8 electrons, which would be a violation of the octet rule, I need to use another electron orbital, and that would be the d orbital. And so phosphorus and beyond, we can have more than 8 valence electrons because we have access to empty d orbitals. So what is the Lewis structure for phosphorus pentafluoride? And to answer that question, the first step, how many valence electrons do we have to assign? So step 1, determine the total valence electrons for phosphorus. So phosphorus is neon, 3s2, 3p3. And fluorine, I've got 5 fluorines, and fluorine is helium, 2s2, 2p5. So I have 5 electrons from phosphorus. I have 7 times 5 electrons from fluorine, right? 5 fluorines, 7 electrons each, for a total of 35 electrons from fluorine. I have to assign 40 electrons. So I'm going to place my phosphorus in the center, and then I'm going to surround that with my 5 fluorines. So I just assigned 10 electrons, right? I've got 40 electrons. 10 are bonding electrons, so I've got 30 electrons remaining. I'm going to place my fluorines, 1, 2, 3, 4, and my 5 fluorines. And now I want to fill the octet for the surrounding atoms. So I'm going to place 6 electrons here, and that fills the octet for fluorine. 6 more electrons here for 12. 6 more here is 18. 6 more here is 24. And then 6 more here would be 30. So I've assigned all 30 electrons that I have. If I take a look at the central phosphorus the central phosphorus has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the central phosphorus has 10 electrons in its outer shell. That's more than 8. That's more than the octet allows for. But that's fine because phosphorus has access to d orbitals. So phosphorus can violate the octet rule. So the important things from today, right? Lewis structures of atoms, of ions, Lewis structures for ionic compounds, molecular compounds, determining formal charge, and using that information, using the formal charge to determine the best Lewis structure possible, and then knowing the violations to the octet rule.